Hi, and welcome to another video on thunderstorms. Once again, we're working our way through the different classification schemes. Specifically, right now we're looking at cell configuration. And in this video, we're going to talk about squall lines, what we call multi-cell line storms. And here's the strict definition of multi-cell line storm. It's a line of active thunderstorms. It could be continuous, might have some breaks, but you'll have also areas contiguous precipitation that are a result of thunderstorms. So the difference between multi-cell line and multi-cell clusters is that a multi-cell line is in a line. It has a larger length to width ratio, so it's very long and very narrow. Now when they say contiguous areas, that means that typically what happens as a squall line gets older, it starts to create a cold pool on the backside, and you'll see the precipitation start to spread over a larger area behind the main storm. So they're saying that that is also part of the squall line. Typically, squall lines are triggered by some sort of linear feature, something that's along a line, of course. So that could be fronts, as you see in this example. On this particular day in 2017, you can see that there was a front that stretched from Minneapolis all the way down to Texas, and along a significant portion of that line, close to Minneapolis all the way down to Oklahoma, there was a squall line, and that's what you saw on the previous slide, all the thunderstorms that went from Minnesota down to Oklahoma. But there are other things that can kick off squall lines, and things like dry lines, and we do see a dry line here also, or also surface troughs or upper level weather systems. So there's a lot of different things, but they have to be typically linear in feature. And of course, they form in the maritime tropical air, the warm sector, where the temperatures are warmer and there's lots of moisture. On this particular day, going back to this day again, once again, this is earlier before the squall line formed, and you can see the front, of course, stretching from up near Grand Forks all the way down to Texas. The warm front, there's a couple of warm fronts, but they're separating the warm, moist air that's coming up from the Gulf of Mexico from that cold Canadian air. So that's where you're going to see the storms form. And we have talked about instability in this class, and one of the measures of instability is CAPE. So here are the CAPE values for this particular day, and you see the warm, moist air is flowing up out ahead of the cold front, and that's setting off the conditions that are ripe for the formation of thunderstorms. So here you have values of CAPE that are 1,000 to 2,000 joules per kilogram, which means that you could see some severe weather on this day. And there were about 80 tornadoes across the central part of the United States. So, yep, we got linear features that kick off the squall line. And the squall line or the multi-cells develop typically in a sheared environment. And the shear is a little bit different than the multi-cell clusters, and also a little bit different than the supercell. We'll get to the supercell a little bit. But because you have a sheared atmosphere, that means that the line will last a long time. This is kind of an artist's rendition or version of what a squall line looks like. The updrafts and downdrafts coexist. It's a little bit different than the multi-cell cluster. Remember with the multi-cell cluster, we saw that the air was coming in kind of from behind or the back. In this case, the inflow into the storm is coming from in front of the storm and the same direction that it's propagating. So you can think of it almost like a vacuum cleaner, an upright vacuum cleaner where it's kind of sucking up everything and then dumping all the dirt in the bag in the back. So that's what I like to call the squall line. It's the Hoover vacuum of the air. You can see also that the updraft tends to be pretty erect. It doesn't really tilt too much until you get kind of in the back. And after that cold pool develops on the backside, cold air because of the downdraft, the updraft will tilt a little bit more and you'll get more precipitation on the backside. So, of course, the squall line or the multi-cell line feeds warm, humid air from out front. It gobbles it up. Precipitation falls out the back, And as precipitation falls, you get melting of hailstones or ice crystals. That cools the air and you get a downdraft. So on the backside, you get the downdraft. Sometimes if the conditions are just right, you might have environmental air, meaning dry air moving in from the rear and entering the downdraft. And that will help evaporate some of the precipitation, which causes the precipitation descent or the downdraft to descend faster because it's cooler, and you get a strong gust front. And that gust front kind of undercuts the updraft, but it doesn't kill it. It actually acts as a lifting mechanism, and sometimes what you'll see is a shelf cloud. That is the indication of the interface between the cold air flowing out of the thunderstorm and the warm, moist air flowing into the thunderstorm. So that cold air, that gust front, provides a constant lifting mechanism to get the air to reach saturation and release latent heat. And as I mentioned, on the backside of the storm, you can always tell older storms, older squall lines, because they tend to have a wider area of precipitation. Just like humans, as we get older, we get wider. Same thing with squall lines. As they get older, they get wider. As I mentioned that environmental air, dry environmental air coming in from the back of the storm, then that mixes with the downdraft. That's called, in meteorology, we call that a rear inflow jet. That happens at mid-levels, typically at about perhaps 15 to 20,000 feet if the winds are strong. And when you get a strong rear inflow jet, it can create some really strong straight line winds. Those strong straight line winds sometimes cause the squall line to bow, and you get something called a bow echo. And so the bow echo is an indication of strong straight line winds at the ground. Here's a picture or radar image of the Bismarck radar right before bow echo hit. This is back in 2011. And in the upper right, this is as it's just hitting the radar, so it's about a few minutes later. And I pulled up some METARs for that particular day. So as the bow echo or the squall line went through, you can see that, of course, the visibility dropped significantly. And then also the winds picked up quite a bit. And before the line went through, the winds were at 17 knots, and afterwards they're gusting to 44. So there's a significant increase in wind speed. If there are breaks in the line, typically that means that those storms on the south side of that line where the break is won't be competing with the other storms for moisture coming up and feeding the storms. So you tend to have stronger storms in that area, and also perhaps a chance of tornadoes in that region. Also, you can see here's another cross section going from A to B, and you can see it has the characteristics where it's sucking up air up front and then dumping the precipitation out of the back. So you have this continuous strong radar return indicating precipitation falling. And it's not a descending core because it's continually being fed with new precipitation particles. Like we did with the other types of storms, I took an example. Here's an example. We're going to look at a storm that went through Bismarck. Bismarck tends to get a lot of squall lines. So here's one that went through back in 2003. And it had already gone through Bismarck and it's moving off to the east. What we're going to do is we're going to take a cross section from point A to point B and look at the storm. And the storm is at about, in this case, close to about 3,000 feet on this radar image. But once again, if you go higher, remember as you go higher, this is about where the freezing level is, and you're getting strong radar returns. Of course, that's what you'd expect. As you go even higher at 33,000 feet, typically where airliners fly, you can see that there are towers going up, and it would be difficult to circumnavigate these. You'd probably have to fly around the entire line instead of trying to pick your way through little cells. Here's the sounding for that particular day. You can see the freezing level was at about 13,500 feet, and the tropopause was up at close to 40,000 feet. And here's the cross section. You can see the storms are going well above 42,000 feet. We said that the tropopause was about 40,000, so this is a vicious storm. It's going up well above the tropopause. You can see the red extending from 42,000 feet all the way down to the surface, which is just intense. And then also you can see the anvil spreading out ahead of the storm. It's really hard to kind of envision the updraft, but it's in that green area kind of, and the precipitation is falling back in that red area. And then you can see the green starting to spread on the backside, telling you that the storm's getting a little bit older. So those are squall lines. The next video that we'll have is supercells, so stick around.